the earlier video we have looked at the Cantor network and then came up with the computational cross point complexity for a strictly non-blocking switch, how much minimum actually we can achieve, and thereafter then we moved over to wide sense non-blocking switch configuration. We have taken a switch, we have actually made the complete state diagram. We in fact also did exercise on how to actually find out the non-equivalent states, and what do we mean by equivalent states, we actually understood that, and using those non-equivalent states we had built an state diagram, and then we also understood that if we actually avoid transitioning through certain possible state transitions, then I will never ever be moving into a blocked state and switch will always remain strictly non-blocking. So, but this requires an operational algorithm, we actually in fact understood that, and that was a 4x4 simple switch, and what we did was instead of actually having 3 stages of 2 switches each, we had 4 stages in this case. So, this all when we were talking about, we were actually trying to look into a cross connection technically, looking into the inputs and outputs, and we were trying to create the paths, that is what we were doing, and whenever we are trying to see if a free input port is there, output port is there, whether I can set up the path or not. But as actually we have progressed, we have slowly have been moved to something very popularly known as voice over IP. So, we use internet packets or IP packets for transporting the real time traffic. Okay. So, now I am actually moving over to something what we call packet switching. So far what we had done was all the basics which actually can be used for circuit switching, has been used for circuit switching for a long time. Now we will be looking into something called packet switching systems. So, but what is this circuit switching and packet switching? So, let me explain why the packet switching is so lucrative now. In fact, the concept of packet switching was known long time back. In fact, internet was working using packet switching long time back, but there was no voice being moving over that system. It is only now that voice and live video streams actually have been moving over a internet network. So, why that is actually happening? So, the reason for this, before to understand this, we need to understand what are the delay components in a circuit switching system and what are the delay components in a packet switching system. So, if you look at circuit, so I am taking a very simple example that we have 4 switches and the information has to go from first to the fourth. So, there are 3 hops in this case, and these vertical lines will indicate the time. So, as I am moving down, my time is increasing. Okay. So, normally when I am talking about a circuit switching scenario, we will first of all make a request to set up a path all the way from source to destination. So, request will be going from switch 1 to the switch 2 and they will configure the path. Then this will also look for resources, it will also configure the path, this will also configure the path. Once the path is done all through, then the confirmation has to come back. So, normally a confirmation will be coming back. And once the confirmation here, then I can actually start transmitting. So, whatever I am actually gathering as a information, for example, if it is a microphone on this machine and it is capturing an audio. So, every 125 microsecond 1 octet will be generated and that octet can simply be pushed through. So, the path is already set up. So, it is like a pipe which has been created, just be pushing in the byte will go all the way the other side and it will come out. Routing action actually has been done here itself, only once path setup is being confirmed and now you start doing transaction. You start doing transaction byte by byte. As you are generating more and more bytes, you are transmitting, information is reaching here, and as you are receiving the information, you are playing it back. So, only delay which happens from source to destination in this case is this. Now this technically is whatever is a propagation delay in the first hop, then there is a propagation delay in the second hop gets added, then propagation in the third hop. So this delay is propagation delay 3 times of that, which is going to happen in this scenario, and information is available. Whenever you want to disengage the circuit, that time either from this side you will tell and the disengagement will happen, or from this side a disengagement message actually can come up through the switches. Either of these, this or this can happen, and connection can be dismantled. So there is a circuit setup delay which is involved in between before you transit. Now what happens in a packet switching system? Now of course before I move to packet switching, what is the problem here? So you can actually list down the problems. The first problem is your circuit setup delay is pretty high. Okay. So once you set up a circuit, then only you can transfer the information. Second thing which happens, when you actually have set up a circuit, after this, even if I am not speaking, my bandwidth is going to be reserved for me. That whole path is reserved for me. So bandwidth will not be used if I am not communicating. And typically in voice communication, when two people are communicating, one of them will be listening, other one will be speaking, and these roles will keep on changing actually. Okay. So 50% of the bandwidth actually goes waste immediately there itself, and then people will have pauses in between when they are speaking. So they will also be losing bandwidth at that point of time. So very small actually will be utilized. So it is very inefficient system in that sense. Okay. And there is another problem, because if the link actually fails, then what will happen? The whole path is now gone, it has to be reset again before you can transmit the data. It has to be recreated again. Okay. So resilience actually is missing. This resilience was built in internet when the packet network actually were implemented, but they were not for real time traffic. But the resilience is because I am not setting up any path. What I am doing is I am trying to create a small information packet, and this basically here, let me complete this stuff. Inefficient use. So BW stands for bandwidth. And of course recovery does take a lot of time. So when number of hops are very large, the probability of failure in any one of the link actually becomes pretty high, and then recovery will take a lot of time. So we need to move to something called packet switching, which is a different mode of communication. The idea here is, at the source, as I am speaking, it will collect the information. After the information is collected, it will actually put all the information, a chunk of bytes. So there has to be proper encoding. Then I will attach an header. I can also optionally attach a trailer, and this is what I have formed a packet actually. Okay. So packet, this is the first bit which will be transmitted and so on, and this will be the last bit which will be transmitted. Okay. So in this case, the header, I have not set up a packet a path beforehand. So how the packet will know that where to go? Here path has already been set up. So when I am sending chunk of bytes, I am not attaching any information. They just pass through. It's like being a pipeline being created from source to destination. In this case, there is no circuit setup being done. So this header will actually contain additional information. So there I was only sending the information part, which probably may be my voice samples, but here I am also sending something extra after every collection of chunk of these bytes. So this is what is known as packet, and this header normally will contain a destination address, this will contain source address, there may be parity check. Parity check normally is done in the trailer, but it can be there also in the header, or checksum. We can actually have many other fields, IP headers actually do provide them. Quality of service tag. So different packets can be treated differently in the network whenever there are problems or whenever the priority has to be given. So we have quality of service field which can be there. We do provide sequence number, so the packets can be played back in sequence, okay. So you cannot have out of sequence stuff. And of course we may have an identifier which says that when the packet is received, so which particular program or software the packets or the chunk of bytes have to be passed on to. So there can be multiple. So internet protocol typically has this particular field which says which protocol it has to be handed over to, okay. So identifier for higher level entity. So once you have a packet which has to be done, and this is typically will be the format. If I draw the same thing, let me do it with a different color, how it will look like. So this circuit setup phase is gone. Now I will actually first of all start collecting my voice samples. Once I have sufficient amount of data collected, okay, then my packet can actually be framed. So now I will actually create an header, create a trailer, and I can start transmitting the packet. So this is the first bit which has gone, and this is the last bit which has gone, and packet has been completely received at this node at this point of time. Now this delay when the packet is being formed is known as packetization delay. Okay, and this time is known as transmission delay. Okay, and then we will have, as usual, the time which is required. This is the propagation delay. So this of course you cannot do much. This is the material, this is the system property. As you move, you will take time. Roughly it will be speed of light in divided by 1.5 in case of optical fiber. So you will be roughly going by 3 divided by 1.5, which is about 2 into 10 to the power 8 meter per second. That will be the speed. So in fact this time, propagation time, will be very small in most of the systems. So but the problem here is, next guy cannot actually transmit these bytes as it is. Remember when the bytes was coming, they were being transmitted, it was like a pipe. Here you cannot do it. You have to receive the complete packet first, analyze if the parity is okay or not okay, if there is a packet has been corrupted or not. If it is corrupted, you have to drop it actually. If it is not and everything has been checked, then you look into the header, find out the destination address, and it will maintain its own local routing table. It will search into the routing table, find out to which outgoing line it has to go. I have only shown one, but this might be connected to some other nodes also. So it is to figure out where it has to go. Earlier also when the circuit was being set up we were doing this, but it was done only during circuit setup phase. Okay. So we need to transmit from here all the way again the whole packet. So the packet will be completely received here again. So I will have a small amount of delay here which I will call TH, it is a header processing delay. So we will actually have the complete packet will be received here, then it will be transmitted. Finally packet is transmitted here. So whatever is the voice chunks bytes which have come in, they have to be put in a buffer. Meanwhile another packet will be coming and thus that packet will be put in the buffer and the playback will be done. Okay. So every 125 microsecond 1 octet has to be played back. If you do not have bytes in your buffer, you have to be just silent at that point of time, or you skip that much of the voice. But if you are getting too many chunks, you have to keep on buffering them, you can't do much. Okay. So the packet will be reaching here. Now what will be the delay when you will be using circuit switching and packet switching? Let us look at this. For circuit switching, the delay will be, so if there are, in this case there are 3 hops, so T delay in this case, if there are n hops, will be nothing but if Tp is the propagation delay only in 1 hop. So this actually delay here will be 3 into Tp, which I have written here. Here every time this, so it will be n into Tp, that is the only delay which will be there in circuit switching system. While if you look into the packet switching, which I will draw with a different color. So in this case you will have a packetization delay Tp, which, okay, let me, because this Tp we will confuse, so I am going to put propagation as TPR, propagation delay. Okay. So I am just changing the symbol. This is packetization delay. Yeah, I have written there. So one packet plus the transmission delay. Since there are n hops, so n times the packet will be transmitted, plus the header processing delay n times, plus n times TPR. So the amount of delay which you will actually have extra in case of a circuit switching system, in a packet switching system, this is the extra delay which you will be incurring. So if you want to actually have a real time voice transport or real time video transport, this actually should be as less as possible. Now in the earlier days, in internet was actually packet switch based, but the bit rates which were used in the systems were much smaller. We were not having optical fiber at that point of time. So as a consequence, transmission delay was pretty large. Our processors or routers were not very fast. So header processing, which means you are going to search through this table, decide and then make an action, set up your switch. These particular things were very large. So for very large number of hops, you will not be able to transport your voice or any real time traffic. So for real time traffic, circuit switching was the case. In fact, that is the reason why for a long time we actually had a separate telephony network which was circuit switched and a separate internet network which was packet switched. But of course, over time we have our bandwidths actually have increased. So my transmission time, if my number of bits in a packet are B and my bit rate is R, so amount of time which is required is B by R. If my R is very large, which now we actually operate at gigabit per second, we operate 10 Gbps, 40 Gbps and higher. So this time becomes extremely small. Okay, this magnitude of orders actually it has gone down, and because of this time is becomes very small. We actually have started at some point of time started using very short packets, we call them asynchronous transfer mode ATM packets. They were used to be 53 byte frames actually. In that case, internet protocol or IP protocol does not use short length packets, it actually does allow variable length ones, and the length can be very large. Okay. So, if we use short length packets, packetization delay will also be small. Remember, if I have to even collect 10 bytes, I have to wait for 10 into 125 microseconds before I get 10 voice samples to make a payload. Okay. My switching technology actually has been improving. I have better processors and better memories, so I can do much faster header processing. In fact, this still remains a challenge. So, that is the reason why now we have been actually trying to move something what we call optical bus switching, where many multiple packets are being put together and then there is only one header. So, you have to process only one header for large number of packets instead of processing large number of headers. So, of course, this has gone down and now we can have voice over IP because of this. Okay. So, now it is because of high bandwidth and better processing capacity that we are able to actually have this technique. In fact, even with packet switching, for a real time traffic there was a problem. I was not able to process large number of packets. So, people came up with something called multi protocol label switching. Okay. So, there are multiple packets being identified, this technically something called virtual circuit switching. So, in fact, when I look, a packet comes to me, I will actually not look into the complete routing table, I will set up a virtual path. I will actually create this tag will be coming, this packet has to move to this guy and this tag has to be modified to this tag. So, I will only maintain what are the flows which are going, but they are always going in small chunks which we call them frames or packets. Okay. So, multi protocol label switching essentially improves my performance of the switches. So, this is the reason why packet switching is now much more lucrative. Let us see how we can actually build this. So, one of the most common things, I think all of you will figure it out, all of you will say, okay, let us take a PC, put multiple cards inside that and let the packets come from one card and I will have a software which will do all the analysis and it can be pushed out on another card. Now, this has a limitation. In fact, we used to call this as a router earlier. So, you have a PC which has a processor or board and then I have lot of interface cards and these interface cards are being connected to the outside world. So, packets can come in and go out. So, these can be Ethernet interface cards or something else, but this central processor maintains the routing table, there is a Linux kernel or whatever it is, and every packet which comes in has to be analyzed and then pushed out, and there are actually input buffers which have been and output buffers being maintained across this. Normally this kind of routers will perform very poorly. So, if you take a PC and put multiple cards and put drivers and try to build up a router, it is okay for lab, for a small load, but not for very high speed performance. This actually is not going to work, we have to change the design. So, how we can actually build a design? So, that is a question now. So, now remember I had talked about crossbar, can I use a crossbar for doing this job? But you will again ask a question that IP packets are variable length packets, how this actually can be done. So, okay, let us relax this condition that all packets which I will be switching will be of fixed length. How IP packets will be switched, I will come to that. Okay, there has to be way for even handling that. So, if that is possible, I can actually take a crossbar and I have inputs and I have a slots. These slots are synchronized at all the inputs and I have the outputs, and then what I can happen is the packets will be coming only in this slot, these are fixed length packets, and these packets I can actually tap and for when these packets will be coming, based on that I can decide what will be crossbar state, which packet should be going to which outgoing port, and I will decide, I will set up a circuit through this crossbar so that these packets will go to specific designated ports wherever they want to go. Okay. And once these packets are out, for the next slot which will be coming, I will again set up this configuration. So every slot I am going to change my crossbar. So it's not like voice circuit, for the whole voice duration the circuit has been set up. So every slot I am actually changing it. So I will be able to do now packet switching, and this will be much faster than what we will do with a router, which is based on a PC with multiple interface cards. Okay. So idea is that you now look into the headers of all these packets. These has to be analyzed by somebody. A map has to be decided how the crossbar is going to operate. It has to actually exert the control, that row and column control. Once that is done, then by the time the packet will be coming up, packet will be passing out to the output, and then the next set of packets will be coming in. Again the same procedure, you will keep on doing it. Now one important observation which you can see is that all the headers which are coming, I should be analyzing all the headers to decide the connection map. I need to finish all the header analysis within one slot, because then in the next slot again same number of headers will be coming. So number of headers coming per slot will be equal to number of incoming ports. So this processor ultimately will now lead to limitation of this switch performance, because now I have to process n number of headers per slot. So you cannot actually increase this size arbitrarily, but of course we have ways by which we can use multiple small crossbars and then create a interconnection network for packet switching. So it's like the way we did in circuit switching. We had initially a small crossbar, then we moved to 3-stage interconnection network. Same we can do with the packet switching to alleviate from the problem of, or the bottleneck of this particular processor, to actually take care of that. So now typically what will happen is, there will be something called network, there has to be interface board on the crossbar, so that when the packet comes in, the header has to be tapped, header has to be then communicated, should be made available to the processor, packet has to be held there, so that there is sufficient time in which the processing is done, cross connection is set up, and then only packet should be pushed into the switch. So we will be actually having a interface board here. Now these interface boards also has another important function, so that I can handle the variable length packets. I will come to that. So I am just drawing a 4x4, these are interface boards. This is a crossbar, and I will actually have one control line through which I will get all the header information, controller will get, and then it will exert row and column control on this crossbar to set up the things. So in this case the headers will be retrieved from here and they will be analyzed here, and packets will be stored for one slot, so that by the time these headers have been analyzed and switch has been set up, and then the packets will be pushed out, next packet will be coming in, their headers will be analyzed, it will again take one full slot, and next queue of next group of packets will be again stored for one slot. So at least one slot delay will always be there in this. So one slot plus propagation delay in this case will be present in this crossbar, and this will be the controller, which will be ultimately the limiting factor now for the switch performance. Now as I have asked the question, if I am going to use IP packets, how I will handle them? Okay. So what I will do is, I will also put up an interface board here So whenever a large packet will be coming, a variable length packet, this packets will be sliced into lot of smaller fragments, we call them frames. So a bigger packet will come, I will slice them into frames actually. So maybe a frame where some of them will be, bytes will be just padded, so that all of them are fixed length frames. So this is what it is going to do, it is going to put in each one of these frames it will add some bytes which will say sequence number, which is the last guy. So they all belong to the same packet, all kind of identifier, and then these fixed length frames, that is what will be switched out. So all these frames for belonging to same variable length packet will be passed into the same interface board. So it will, this outgoing interface board will identify that all the frames which have been received belong to same packet, it will just assemble back the whole IP packet and send it further. So when you are actually seeing, you are seeing this box, you will never realize that inside this crossbar actually is switching fixed length frames, it is not switching the variable length packets. So variable length packets have been converted to fixed length frames by the interface boards into the in the input side, and from back from those fixed length frames to the variable length packets at the output side. Okay. So this is how the variable length packets actually can be handled.